So I'm going over the answers to the homework.
What are we doing after the homework?
After the homework, we're going to, I'll show you how to start the car analysis, and then you're just going to be doing that.
Okay.
And as soon as we've thought over the cars good and well, then you'll have time to improve them. Good and well. Ooh, excuse me, I don't know what I should have said there. Well. All right, so check your answers. If I'm going too fast and you want to slow me down, feel free, but I'll try to just go at a reasonable pace. The thing with the most mass is E because it's got the most stuff in it. It's not the biggest, but it's got the most mass. Greatest volume is D because it's the biggest one. Weighs the least, that's going to be B because it has the least mass. So gravity pulls on matter, and the more matter you have, the more you're going to weigh. Number 4, weight is the force of gravity. Number 5, I didn't show any of my work here. It's pretty straightforward. If you want to know the force acting on a car, you can use Newton's second law, F equals ma. And the mass is 1,000 kilograms. The acceleration of the car is 6 meters per second squared. Multiply them together and you get newtons, 6,000 newtons. On planet Y, I've written the same formula 2 different ways. People in other classes had some confusion between, they said, wait, I didn't mean to say wait there. They meant, hold on a moment. Force equals ma. I thought that was the equation, but then when you're doing weight, it's mg, and I was using these interchangeably. They are the same. Weight is just a specific kind of force, and g is just a specific kind of acceleration. This is the acceleration of gravity. This is the force of gravity. They really mean the same thing. But when people are calculating weight and writing out their formulas carefully, they often write this. So it's just whatever somebody's mass is times their acceleration, you get 80 newtons. And make sure for every time I ask you for a force, unless I specify otherwise, multiply kilograms times meters per second squared. With your cars, we're going to measure them in grams, but you've got to convert to kilograms. This one, there's 35 Newton net force to the left, meaning that this person's pulling 35 newtons harder than that person is. With the car, these 2 forces are the same, they're balanced, so there's 0 newtons of net force. Does that mean the car stops? It means if the car is already stopped, it stays stopped. If the car is already moving, it stays moving. No net force or balance forces just means the motion doesn't change. Whatever it's doing, it keeps on. This next one, when you jump out of a plane, before you reach terminal velocity, your weight is greater than air resistance. That's the right answer to that. I think a number of people had that wrong, and I've got a little diagram up here I keep changing to make this work. So if I want to show somebody who is at terminal velocity, I'm going to make an 800 Newton force, which is the air, or I'm just going to call it the wind, pushing up. And you've also got an 800 Newton force of gravity pushing you down. Those are balanced, so this person's not going to go any faster. It's when you jump out of a plane, when you just start moving, how fast is the wind going past you? Let's say I'm stepping off of a cliff right now. I've dug a giant hole in this room, and I step in. Right now, how fast is the air going past me? It's not. So it's not pushing at all. So in the beginning, when you jump out of a plane, the force of the wind pushing up on you is going to be 0 newtons. And because of that, you're going to have a really strong downward net force because the gravitational pull on your body is much stronger than the wind. But as you go faster, it's like sticking your hand out of a car window. You feel the air pushing you. It might push with 10 newtons when you go faster. And then after a little while, maybe the force of the wind is 200 newtons. But it's still less than this, so you're going to keep going down. Eventually, when you get up to 120 miles per hour, that's when whatever your weight is, the force of gravity, air is going to be just about the same, and then you stop. So the question, before you reach terminal velocity, your weight is greater than air resistance. This number is greater than that before terminal velocity. These? What's so funny over there? Man, these questions, I wrote some kind of confusing looking notes here. What I was trying to say is, anytime there's a change in motion, that means you've got unbalanced forces. Anytime there is no change in motion, you've got balanced forces. If you just keep that in mind, change in motion means unbalanced, you can do it. So situation A, somebody sits here for 5 hours. Is their motion changing? No, they're sitting, they continue to sit, nothing's changing, so the forces are balanced. From A to B, somebody's speeding up and turning at the same time. That's all sorts of changes. It's change in speed, change in direction, so it's unbalanced. This is the one that gets people. From B to C, the speed is constant, 60 miles per hour the whole time. Is the motion changing? Yeah, it's not changing in speed, but the direction is changing. If I were to draw a little diagram of, if this were a race car, we're looking at the race car from above. It's a really bad race car, but those are the wheels. This would be kind of like this. There's the wind is pushing it backward, the motor's pushing it forward. Those two things are equal. There's a really strong force pushing it that way and maybe a weak force pushing it that way. So what I've drawn here, these two kind of cancel each other out. But here we've got an imbalance, and what's going to happen is the car is going to turn. So anytime you have something turning, that tells you there's some unbalanced force pushing it in that direction. If that force were balanced out by somebody turning the steering wheel the other way, then it would just go in a straight line. So any change in motion, unbalanced. From here to here, constant speed in a straight line, is the motion changing then? If we're going the same speed in the same direction, is anything changing? Nothing's changing. So that's balanced. And then the last one, slowing down in a straight line, unbalanced. So really the only two ways you can have balanced forces on you is to either sit still and not move, or to go the same speed in a straight line, unchanging. Number 14, I noticed a lot of people missed this. This was a really easy question if you didn't focus on the confusing parts. The most important thing is that it says a ball is motionless on the ground. So without going any further, if it's motionless, are the forces on it balanced or unbalanced? Balanced. So there's no net force. The question is, what's the net force? It's 0 newtons. There is no net force. And I drew a little diagram to show that, yes, gravity's pulling the ball down, and yes, the ground is pushing the ball up, but those two things are balanced. If it's sitting still, you don't really need to know anything about gravity. You just know that there are no unbalanced forces. Now with the person, all I did in all these, I just used Newton's second law to multiply the mass times the acceleration, and I got my number here. And the answer is it's a force in newtons. And then I look to see whether it's positive or negative. If it's positive, that means there's a force to the right, a net force to the right. And in this first example, it's a 180 newton force to the right. The net force tells me which of these two forces is stronger, and it tells me how much stronger. So pointing to the right, that means this is stronger by 180 newtons, which means that has to be 20. For the next one, mass times acceleration is 100 newtons. Again, it's positive, so it's to the right. That means this force is 100 newtons more than that force. So I had to come up with something that's 100 less than that. Just subtract 100. Now we get to a little complication. -2 times 50, you get -100. And now my arrow's going the other way. That means the net force is to the left, which means this force is 100 more than that force. And 200 is the number that's 100 more than 100. Same thing here, you've got a negative acceleration. Now, does this mean the person is moonwalking backward? If you have a negative acceleration, does that mean the person is actually moving to the left? Could be, or it could be that they're just slowing down. It could be the person is going this way like 6 meters per second, and after 1 second they're only going to be going 4.5. And then after another second, they're only going to be going 4. So it could be they're going this way and slowing down. It could be they're like Michael Jackson and they're accelerating that way, like Michael Jackson used to do. His forces are balanced on Michael Jackson right now. Oh, crap. I was just checking to see if I started the video. There's no net force on Michael Jackson at the moment, as far as I know. Although pieces of him may be traveling around for all, yeah, I wouldn't be surprised. Back to this. So the net force is negative 150, which means 150 to the left, which means that's 150 more than this, so this has to be 200. This one was an easy one, unless you got confused. The acceleration is nothing, so that automatically tells you these two forces are balanced. You could go through the multiplication, mass times acceleration, you get 0 newtons net force, and these things fighting one another have to cancel out. So, you know, they're both 600. Finally, 160 newtons for the net force to the right. That means this plus 160 has to give you that. That's it. Any questions? Okay, stop that.